Now in this lecture, we shall be discussing about how we can model the steel structures and how we can plan the structural steel modeling. So before we start doing the practical real life structures, we should have a basic idea of how exactly are the different kinds of, we can say, structural systems in the uh, uh, we can say Australia that is being implemented. So let us say one of the classic example is the maintenance steel platform that is highly used in the mining structures, so or in the industrial structures also. So here you can see that how the industrial platform is made and how they model the staircase so that a person can go on the top and do the maintenance on the top. And this is the, we can say, another 3D isometric view, and this is the actual the picture of what they have done on the site. Now the important thing that you do need to understand here is that how we can model the structural system arrangement. That is very important. So you know we shall start actually doing the actual model in the ETABS software. So we can select metric SA, Australian, New Zealand, AS4100 and AS3600 as the steel and concrete design code respectively. We can left click on OK, and let us say that the spacing of grids in X meter is approximately 6 meters, and in Y let us assume that it is 4 meter. Sorry, number of grid lines are 2 only, and spacing of grids in X direction is 6, and in Y direction it is 4 meter. Number of story we can select it as 1, and let us assume the height of this platform that we were discussing is approximately 4 meters. So we can left click on OK here. So the first important thing that you do need to understand here is that first of all we do need to define the materials in the software. So here we can see that thickness is between 11 to 17 mm, and as per the AS3679, and grade is 300 MPa. So we can add new materials also, thickness for less than 11 mm also. Here we can see that the yield stress is to 320 MPa, that is higher as compared to the 300 grade steel. And we can left click on OK, and we can add one more material here, that is for thickness greater than 17 mm. Left click on OK, and then again left click on OK. Now we do need to go to the define section properties and frame sections, and in here we do need to left click on import new properties, and under the steel we do need to select the I and wide flange section. So as of now we can select T less than 11 mm, and we can select 200 UB 18.2. After that we can select 250 UB 25.7, and after that we can select 310 UB 32 kg per running meter, and after that we can select 360 UB 44.7. So now you do need to understand that we have 4 different type of sections. First section having 200 mm depth and 18.2 kg per running meter. Second section is 250 depth section, which is having 25.7 kg per running meter. Third section is 310, which is having 32 kg per running meter, and fourth one is 360 depth section, which is having unit weight of 44.7 kg per running meter. So we do have various type of section with various kind of thicknesses. Now one of the mistake that a new engineer do, what they usually do is that they try to select the let us say we do have this 250 and 310. So considering 250, and here we do have 25.7 kg per running meter, but we do have 250 UB 31.4 or 37.3 kg per running meter also. So if we are going to select 37.3 kg per running meter, it is better to opt for 310, which is having 32 kg per running meter, because we shall be having much more, we can say, sectional modulus and second moment of area for this case. So that is the thing that you do need to understand. And as a rule, what we do need to do while selecting the possible structural steel sections is that we can select different we can say properties, and on the basis of the design calculation requirement we can increase or decrease the sizes and unit weight of the section. So we can left click on OK as of now, and we can go to the draw beam column brace, and we can left click on quick draw columns option here. So under the property section, we can select, let us say the column section we can select as 360 UB and 44.7. And if we are modeling this steel section here, you can see that orientation is now we can say horizontal. Now this is the main concept that you do need to understand when we are doing the structural steel modeling, is that considering this particular criteria where we do have a rectangle, this dimension is 4 meter and this dimension is 6 meter. One of them shall be a moment frame, second shall be a shear connection frame. It is always recommended that we should not put our structural steel section like this for the maximum efficiency and optimization. This angle should be something like this, that is approximately 90 degree here. So this is the desirable arrangement of the structural steel columns. So we can select and add 4 columns here. So we can check that in the 3D view also. So this is the 3D view. So we have modeled 4 different, we can say, columns here. After that, what we can do is that we can model the steel beams here also. So we can go to the draw beam column and brace, and we can left click on draw beam column and brace. So here we do have option to select the property here. So we can select, let us say, 250 UB 37.3 kg per running meter. Here we can see that moment release is continuous. The second option that we are getting is the pinned option. Now when we are selecting or adding or connecting the steel beam to the web of the steel column, this is the web of the steel column, we do need to have a shear connection here or a simply supported beam from this point to this point. So the web of the section cannot does not have a capacity to take the bending moment. It only have a capacity to take the axial force and shear forces. So that is why what we have selected here is that we have selected it as pinned connection here. That is, it is pinned from this point to this point, from this point to this point. So similarly we can you add a steel beam here also. So both of these beams are a pinned beams, and how we can check that? We can just switch off this option here, press Ctrl plus W option on a keyboard, select on object assignment and click on end releases and click on sections here also by pressing Ctrl and W option on a keyboard. So the beam that we have selected here is 250 UB 37.3 and it is released from this point to this point. We can left click here and then again right click. So here we can see that end releases are, that is, torsion is released on the first point, that is end I. So this is the end I and this is the end J. So for the structural stability, torsion is not released from both the ends, it is only released from one end. Moment M22 minor axis is also released and major axis is also released. Now some of the engineers do have a conception that we do not need to release the minor axis, we only do need to release the major axis. Now it is up to you. As per my opinion, both the approaches are correct. So we can left click on OK option here. Now we can again go to the draw beam column and brace option here. And then again, instead of the continuous pinned option, we do need to select the continuous option. And we can select 310 UB32 here. Now the thing here is that, when we are considering this particular frame, this is the moment frame here. So we can click on this particular grid intersection point here, or we can go to the draw and snap options. We can select line ends and midpoint, line ends and frame, perpendicular projections and parallels. Left click on apply and close. So we can model the steel beam from this point to this point. Similarly, a steel beam can be just right click to switch off this option. Again, we can left click from this point to this point. Now here we can see that there are no as such end releases provided here. Like here we already provided the end releases, but as this is a moment frame, so there are no as such end releases provided here. And why we have selected higher section as compared to this? This is because this is a moment frame and it has to take care of the bending moment also that is coming. And let us assume that we do have to model like 2 secondary steel beams here also. So what we can do is that we can select this particular beam, press Ctrl and R option on a keyboard, select linear, dx as 2 meters and number as 2. Left click on apply and close. Now these two beams are the simply supported beams. So we can, either we can select the members by this option or by this option. It is always better with that we go from bottom to top, so that whatever members are coming in that rectangle, it automatically gets selected. So we can go to the assign frame and releases in partial fixity. We can release the torsion at one point and moment M22 and M33 on both the points. So apply and close. And then again, draw a rectangle from bottom to top, go to assign frame and section property, and we can select the smaller section here, that is approximately 200 UB and 18.2. So we can left click on close option here. So now this is the standard, steel platform that we have modeled. And what we can do here is that we can apply the loading option here on the top. So to apply the loading option, we can go to the define section properties and slab sections. We can left click on add new property here. Just, we can model a passive membrane. So we can select it as we can say slab, and here we can select it as a membrane. So why we are doing that? So that whatever loading, is coming, that can be easily transferred on the floor. So we can select AS3679, thickness less than 11 mm. It hardly matters because ultimately our intent only is to transfer the load, whatever we are providing, to all the steel members. Now, one thing that we do need to understand here is that either we can provide the one-way action here also, because this is 2 meters and this is 4 meters. So this is a perfectly one-way slab. So we can left click on use special one-way load distribution also, and then left click on OK. And then again left click on OK. So we can go to the draw floor walls and draw floor wall and option here. So here, we can select membrane option here and edge drawing type as what we can say as a straight line. So we can select this point and this point and this point and this point, and then again right click. So now we have modeled a membrane also on the top. And what we can do, we can select the shell and we can select these members here also, and we can go to the edit shells and divide shells. So we can select divide quadrilateral triangles at selected joints and intersection of selected frame objects. So here we can see that now this is a perfect one-way loading that has been assigned here. So we can select all of these three shells here, sorry, membranes here, and we can go to the assigned shell loads and uniform. So here, what we can do is that we can select the live option here. Let us say we apply a live load of 5 kN per meter square. So now if we left click and right click here, we can go to the loads, and here we can see that now the loading has been assigned of 5 kilonewton per meter square. Now this is a simply supported beam, this is simply supported beam, this is also simply supported, and this is basically the moment taking frame here. Now before we run the analysis, we do need to assign the fixed support here also at the bottom. So that is the basic requirement if we are talking about this kind of moment frame and this kind of structural system. So we can go to the assign joint and restraint, and here we can just left click on fixed node here and then apply and OK. So under the advanced set load cases to run, we do need to switch off the model case here. So we do need to left click on this option here and then do not run here, and then we can just run the analysis here. At present, we are just studying about the structural system of the steel buildings so that we can understand how the bending moment and shear force behaves. As per my understanding, for the steel platform that they have made here, this system would have been much better if the orientation would not have been like this. It is always recommended that when we're talking about the plan, and this is the moment frame, this is the shear frame. So it is better that we could have rotated this column here, this could have been the moment frame, this could have been the shear frame, and the steel optimization or steel utilization of this building would have been much lesser as compared to what it would have been, made here. So here we can see that it is having a deflection of approximately minus 0.8 mm. Here also it is minus 0.8 mm. And the important thing that we do need to see here are the bending moment diagram here. So we can go to display force stress diagram and frame Pierce Vanderling forces. So under this option, we can select live load here and then moment M33. So this is the bending moment diagram that, I just want to share with you. Yeah. So here, you can see that this is the perfectly simply supported beam. Obviously, we had released this beam from this point to this point. We can just add new window here. And here we can go to the display and deform shape. So that this is the actual, and this is the what we can say as the bending moment diagram. Now here you can see that when we're connecting the steel beam to steel beam, obviously it should be a shear connection only. It shall not be a moment connection. So here we can see that at this particular point our bending moment is 0, and at the center point we can just left click and right click here. At the center point we do have a maximum bending moment of 20 kN meter, and this is the shear force diagram, and this is basically the loading action that is acting on this particular steel beam. So this is a simply supported beam, and the same case here also. This is also simply supported beam. Now, as this beam is having 2-point load here, 1-point load here, and 1-point load here. So this is the bending moment diagram for a beam which is having 2-point loads here. And here the bending moment is maximum at this particular, we can say point, that is approximately 38.29 kilonewton meter. Now, this is we can say basically a moment frame here. So we can just left click here and then again right click here. So this is the bending moment diagram for a fixed beam. So as we had made this as a what we can say as a moment frame. So this beam here, the bending moment is coming approximately 4.8 kilonewton meter. Same is the case here also. And as you can see that regarding the columns also, the column is also having a bending moment that is like what we can say as having this kind of shape. So this red one is at the bottom, yellow one is at the top. So at the top it is approximately 4.636 kN meter, and at the bottom it is approximately what we can say as the 2.38, approximately 2.4 kilonewton meter. So that is the what we can say as the bending moment diagram for a simply supported beam, for a beam that is having a 2-point load, and for this beam which is fixed on both the ends, and for a column which is fixed at the bottom and fixed at the top. Now similarly we can check the what we can say as the shear force diagram also. So if we want to see the shear force diagram, obviously we are talking about, yeah. So this is the shear force diagram here. So for the beams, if we are checking, this is the shear force diagram for what we can say as the simply supported beam. Same here also. And for a beam which is having 2-point load, this is the shear force diagram. And for a beam that is fixed on both ends, this is the shear force diagram. So I hope the concept is clear to you, and how, as I said, this beam always has to be simply supported because this beam is connected to the steel beam which does not have any capacity to balance the moment. If any engineer is allowing the moment here, he or she is doing wrong. It is always recommended that one frame should be a moment frame. The second frame should be a shear connected frame. So this frame that we have selected here, this is the shear frame. And this frame here that we have selected, this is the moment frame here. Now, I hope the concept is now clear to you regarding the simply supported and the different kinds of beams and columns. Now, let us just unlock this model here. And apply some lateral force here. So we can go to the assign joint and restraint here. Sorry, assign joint loads and force. And here we can select, let us say, 5 kilonewton of the point load on all of these 4 nodes. It may be due to the wind, it may be due to the earthquake, or it may be due to the dynamic action of the equipment that shall be supporting on the top. So let us just understand the behavior here. So we can go to the analyze option here again. So we can see that deflection here is approximately coming as high as 64 mm, and that is a very high deflection here. That is only, when we're talking about the 5 kN point load on all the 4 junctions. So how we can ensure that this particular platform shall be stable at the time of the lateral events, or let us say lateral forces. So let me just unlock this model here. And what we can do, we can just simply Control C and Control V option on a keyboard. Simply copy paste this model, and let us copy it at approximately 10 meters. So let us assume we do need to understand these two models here. So everything is same. Joint load is also same. Properties are also same. I think the properties are not copied. Let me just check. Let us just delete this model here and then press again Control and R option on a keyboard. So here, we can select and ensure that whatever loading is applied here, that are simply replicated here. So here, left click on modify, and here you can see that all the forces, ground temperature, panels, floor meshing, spring restraint, everything is copied. We can just delete this model. Yeah. So now we can go to the define section properties and frame section, and we can select import new properties, and here we can select, let us say, steel angles. Left click on OK. Thickness, let us assume that we are selecting 75 by 75 by 6 mm. Thickness is less than 11 mm only. So we can left click on OK, and we can go to the draw beam column and brace. So in here we can select the angle of 75 by 75 by 6, and moment release we can take it as pinned, because that is, as it is a bracing member only, so we do not need to balance any kind of bending moment at the ends. We just need to balance the axial forces. So this is the cross bracing that we have modeled on this particular frame and on this particular frame. Okay, so let us just check that loading has been replicated or not. So in here we can check that loading has been replicated. So we can again go to the analysis option here. Both the models are same. Here, we are getting a deflection of 64.329 mm. Here we are getting a deflection of only and only 0.299 mm. If you are, concerned that loading is not replicated, we can just go to display and load assigns and join, and here we can select a dead. So here also we have applied 5 kN on all the 4 nodes. Here also we applied 5 kN on all the 4 nodes. And if we see the deform shape under the dead load action, that is the lateral forces, here we are getting 64 mm, and here you are getting only 0.29, and that is negligible deflection. That is the purpose of the bracing, that it is always recommended that, as this is a shear connected frame, in the shear connected frame only we should provide the bracing. In moment frame it is already stronger. It is not that the moment frame do needs a bracing, although it never harms to provide the bracing at the moment frame also, but it blocks the access inside the structure. So as I said, it is always recommended that always add a bracing in the shear connected frame. So in front of you I've shown you that how you can control the lateral sways. So we can go to the display force stress diagram and frame pier spandrel length forces. Case we can select it as dead load itself, and what we can select here is that, yeah. So here, you can see that this is moment 22 is the minor axis bending moment. So in here, you're getting a minor axis bending moment of 18.94. But in here, you're getting a bending moment of 0.1431, because all the lateral forces that were coming here of 5 kN, that has been balanced by this particular bracing member. So whatever, the lateral forces are coming, that has been converted into axial forces here. So in here you can see that 6.4 kN is the axial force here, and 6.05, that is approximately what we can say as a tension force here. So this is in compression and this is in tension. That is the main criteria or main system of why and how the bracing is provided. Now that is one concept. Now let us just try to uh, replicate this again and do one more experiment. Just press Ctrl and R option on a keyboard. Sorry, before that, we just need to unlock the model here and then press Ctrl and R option on a keyboard. In here, we can select the number as 1 and then again select DX as 10 and left click on OK. So what we can do here is that we can change the supporting condition here. What we have done, we have changed the supporting condition on all of these, what we can say as the nodes. We can go to the assign, joint and restraint and just apply the pinned connection here. So this is the third type. Let us just check that whether it can do the analysis or not, because sometimes it do shows the instability here. Okay, so now we do have a third case also. What is the difference in the bending moment at this particular node between case 1, case 2 and case 3? Let us just first of all switch on that. So we can go to display force test diagram and frame pair spandrel link forces. So under this case where we are having a pinned support at the bottom, if we want to see the bending moment at this particular point, so we can increase the scale of this. So again increase just a minute. Yeah, so what we can do is that we can go to the select object type and then just select the columns here. Select and close, right click here and left click on show selected objects only. Yeah, so now it is okay. We can increase the scale again. Yeah, so that is what I wanted to show to you. So in here you can see that this is the bending moment diagram for the same load case, that is live load case only. Here also the bending moment diagram is same, that is it is higher at the top and it is at the bottom also, but the bending moment is getting developed at the fixed support also. Here also it is same, but in here you can see that bending moment is 0 at the bottom. Why? Because we have selected the pinned support. So that is the difference between pinned support at the bottom and fixed support at the bottom. So we can select Ctrl W option again. Sorry, we can press Ctrl Shift and A option on a keyboard so that it switches on everything in the model. So that is the fundamental difference between braced and unbraced frame, moment frame and shear frame, the fixed base at the bottom and pinned base at the bottom. So I hope the concept is clear to you. This was just a basic introduction so that you can understand how the steel structure behaves with bracings, with secondary beams and with primary moment taking frames.